In this lab, we'll reduce water hardness by removing calcium ions using an ion exchange resin, which is a special polymer shaped into porous small beads that have a large surface area. On their surface, along the polymer chain, are functional groups with single negative charges all paired up one-to-one with sodium ions. Because calcium ions have two positive charges, they bond with two of these functional groups. And 2-to-1 is a stronger attraction than 1-to-1. The ion exchange process trades two sodium ions against one calcium ion. The fresh column is filled with sodium chloride solution, and the first step requires to lower that solution until it is just half a centimeter above the top of the column of beads. Next, the burette containing the column is filled with the hard water, which can be tap water, which in Sarnia has about 100 ppm calcium, or with a special solution prepared for you with 500 ppm calcium. Now adjust the drop rate to about 1 to 2 drops per second and allow for about 30 milliliters of your hard water to go to waste. Refill the burette and then with the same drop rate of about 1 to 2 drops per second, collect about 30 milliliters of treated tap water in a clean beaker. To determine the calcium before and after the ion exchange process, we titrate the calcium concentration with the same complexing agent that we've seen for the pipe scale calcium determination, 0.01 molar EDTA solution. A clean burette is conditioned with the 0.01 molar EDTA solution, so we fill it all the way and then discard one complete volume of the burette into a waste beaker. The conditioned burette now has to be filled again, but don't waste time trying to fill it to exactly 0.0 milliliters. Go near the full volume of the burette and then record the initial volume, in this case 4.80 milliliters. To titrate exactly 10 milliliters of the calcium solution, we use a 10 milliliter volumetric pipette and a manual pipette pump. Holding the pipette near its neck, near the top of its neck, we carefully insert it into the pipette pump. Now the pipette is placed into the calcium solution, and by turning the wheel, we can push some solution into the pipette until the lower meniscus of that solution is in line with the calibration line on the pipette's neck. The manual pump has a trigger. When we pull that, we release the solution into an Erlenmeyer flask, and as always, the last drop stays in the tip of the volumetric pipette because it has been calibrated to deliver. The indicator for the calcium titration is again iriochrome black tea, which is red when it bonds with calcium, and it turns blue, dark blue, when the EDTA bonds with all the available calcium and none of it is available for the iriochrome tea anymore. The color change is best observed in basic solution. So we add 4 drops of iriochrome tea, 30-40 milliliters of distilled water, and a dropper full of 6 molar ammonium hydroxide solution, which gives us a nice red calcium solution to start. Now we release the EDTA solution at about 1 drop per second until we notice that the solution starts turning blue, which is when we reduce the rate even more to maybe 1 drop every 5 seconds. We want to determine with great accuracy at what drop the solution finally turns blue, and then By calculating the amount, the volume of EDTA that has been released, we can calculate how much calcium was in our solution. We perform this titration twice, with a solution before and after running it through the ion exchange resin, and that allows us to determine the effectiveness of our ion exchange column.